All right, so in this video, we're going to talk about surface integrals. So we're transitioning from line integrals now to surface integrals. A surface integral, in general, is to a surface in space what a line integral, which we've studied in the past, is to a line or curve in the plane. So they're very analogous when you think about them and how they operate together. So for us, we're going to let S be a smooth surface. It's a parameterized smooth surface with parameters u and v. And we're going to have a continuous surface g of x, y, z defined on S. So the surface integral of g over S. So surface integral of g over S is defined as this guy right here. Now, a couple things to point out. First of all, you can see you have a double integral. That's obviously different than what it was for line integrals. But you also have a capital S here. And so the capital S is going to denote surface. It's a little bit hard to see. For line integrals, we did use a lowercase s, but this one now is an uppercase. And we're going to define it very similar to what we might have in the past, where we've got our surface G being evaluated now at f of u, g of u, h of u. UV, excuse me, f of UV, g of UV, h of UV. And then we're multiplying it by the magnitude of the partial r with respect to u, partial r with respect to v's cross product, and that was what we defined as surface area in the past. And then, of course, we have our dA out here because of the double integral now over region R. All right, so in this example, we're going to take a look at our g being yz, and then over, so we're computing the surface integral of g over this guy right here that lies above this guy right here. And so before we really get into it too much, I do have the formula up here again that we're going to use. We're going to take our g and we're going to evaluate it at f of uv, g of uv, h of uv, which means that we're going to need to parameterize this right here. Additionally, once we parameterize it, we'll need to take those cross products of the partial derivatives and then find their magnitude. So real quick, let me just remind you what this looks like. This is your sphere centered at 0, 0, 0, radius 2, and this is your cone. And so what we're actually studying, and not that this is really important to see, but I think it's going to be helpful, is that ice cream cone looking thing that we've seen in the past, where we've got this top part here being the sphere and lies above the cone that you see right there. So let's go ahead and jump in with the parameterization of this right here. And fortunately, it's really not going to be too bad because this guy right here being a sphere, we've done this before. We've used spherical coordinates. So our r of phi and theta is going to be 2 sine phi cosine theta. We have a 2 sine phi sine theta, and then we have a 2 cosine phi. And again, that comes from the rho sine phi cosine, rho sine phi sine, and rho cosine phi for the z value. So we've done that before. Now, when it comes to the rest of it, we need to make sure we take this into consideration as well. And so what we're interested in is phi being bounded between 0 and pi over 4. So remember, phi starts up here and it drops down. So it's going to start here and it's going to drop down to this angle, which was pi over 4 we've shown in a different video. And then our theta is going to be between 0 and 2 pi, as of course this thing would go all the way around. All right, so now that we have that, really it's just a matter of plugging stuff in. I'll go ahead and start with the magnitude here of this cross product. So r sub phi cross r sub theta is going to be, so this guy here with respect to phi is going to start off as 2 cosine phi cosine theta. Then we'll have a 2 cosine phi sine theta, followed by a negative 2 sine phi. So that was the partial derivative up here with respect to phi. Now we're going to do the partial derivative up here with respect to theta. So this I component underneath the I column will be a negative 2 sine phi sine theta. Then we'll have a 2 sine phi cosine theta, followed by a 0. So when we go ahead and compute this now, again, the identities of sine squareds and cosine squareds are really going to be helpful in all of this. But let me just write out real quick what you're going to get for your vector. You'll get a 4 sine squared phi cosine theta. You'll get a 4 sine squared phi sine theta, followed by a 4 sine phi cosine phi. So now, just as we used the Pythagorean identity, the fundamental Pythagorean identity for several of these, when we find the magnitude, it will also play itself out quite nicely. So if I take the magnitude of this, and I'm going to do this thing squared plus this thing squared plus this thing squared, all square rooted, this actually just comes out to be a 4 sine phi when using those identities. So as we go ahead and drop things in now to our setup, I'm going to have this guy right here evaluated where z is equal to 2 cosine and y is equal to 2 sine phi sine theta. So I'll drop that in for my y value being a 2 sine phi sine theta. My z value was going to be 2 cosine phi. I'll also need now this cross product's magnitude, which was a 4 sine phi, and we're with respect to phi, and we're with respect to theta. Phi, we said, ranged from 0 to pi over 4, and theta ranged from 0 to 2 pi. So this would be your setup then for the surface integral of g over s. And this s, remember, this s was parameterized down here as to what we used. All right, so now we're going to take a look at the case where we're looking for a surface integral of g over s, where s is now no longer a parameterized surface, but your more traditional z equals f of xy. And this f is going to be continuously differentiable over r in the xy plane. And so the setup, you can see, is also pretty similar. Really the only difference is your parameters now in this case are x and y. Therefore, z would equal f of xy. Hence, z equals f of xy up here. And then instead of the magnitude of the cross product, we actually have our other surface area formula with respect to x and y that we saw in the last section. And so the example we're going to take a look at here is to compute the surface integral over g over this right here. Now, to get this set up, it's actually a little bit easier, I think, because you don't have to worry about the cross product and all these other things. But I'll go ahead and I'll drop in here. I know that this guy right here is going to have to be evaluated with xy, f of xy. So when I look at this, my f of xy is going to be y equals 1 minus x. So again, you could do that a couple different ways, but at the end of the day, I'm going to leave it set up like this so that my picture is a little more traditional. So if I go ahead and I set this up now by moving the x over, my y is going to equal 1 minus x. Therefore, when I evaluate x, y, and z, my x is going to be x, my y is going to be 1 minus x, and my z is going to be z. So remember, you're allowed 2 variables or 2 parameters in here, and the way that I've set this up, I've gone ahead and allowed for x's and z's. All right, so now when it comes to the square root, it's going to be 1 plus partial with respect to x, which would be our -1 squared, so that'll be a 1, and then partial with respect to z, which will be our 0. And then we'll have our dz and our dx. And so, again, it's very important to distinguish which parameters you're using. Of course, up here I had x's and y's in the most general sense, but the way I solve this, I've chosen to go with x's and z's. And so just keep track of that when you run those partials in there as well. And then, of course, this would be dz dx. And so the z the z you could see would run from 0 to 1. So we'll put a 0 to 1 there. And then in terms of the x, it's probably easiest if I draw this out. If this is the xy plane, and remember we're talking about over the xy plane, this guy right here is going to be your line with a negative slope and a y-intercept of 1. So we're going to be talking about this. And you can see that x in this case would also run from 0 to 1. So that would be your setup then for this particular line integral, having been given now a non-parameterized surface.